Tony, if you would like to say any introductory remarks, we can get started.
Unmuting there. Thank you, everybody, for joining this morning. Today, we have the pleasure of having Rick Streaker in to talk to us about replacement compressors. The emphasis of today is many of our technicians today want to go out and, when we have an out-of-warranty compressor, they think they need to go directly to the OEM manufacturer to get that compressor. Not necessarily true, and Rick is going to go through a few things with us today to show us, teach us about some compressors and also to show us how to find some replacement compressors. So Rick, thank you very much this morning, and take it away.
I appreciate it, Tony. We appreciate you putting this on. So thanks so much for having us in for this. Just a couple of things. If you have questions today, I like to take the questions while they're fresh in your mind. So please feel free to ask a question. You can raise your hand. There's a little, at the top of the screen, you'll see a little face with a hand on there. And if you press that, that will show us that you have a question. So please feel free to raise your hand. If you're having trouble with that, I have no problems if you just ask your question. Please unmute yourself, though, when you do that so we can hear it, and I'll try and take those as we're going along. So, as I mentioned, this is being recorded, so just be aware of that. So today we're going to talk all about compressors. And when we talk about compressors, we see them in so many different applications. We see them in air conditioning. We see them in heating. Or wait, do we see them in heating? In the case of a heat pump, we'll see compressors used in that. We see them in a lot of refrigeration applications. We can see them in large grocery stores. We see them in small convenience stores. So lots of different applications for compressors used in heating, air conditioning, and refrigeration. Now, when we look at the refrigeration cycle, now, it's called the refrigeration cycle, but it applies to air conditioning as well. And it's a matter of heat transfer. And when we look at the cycle, the heart of the cycle is the compressor. And so the compressor is moving refrigerant through that cycle. And what's occurring then in that cycle is heat transfer. And at different points of the cycle, we have coils in there. And those coils impact the refrigerant that's moving through that cycle. And the compressor is moving that refrigerant throughout that. Now, we're not going to spend a lot of time on exactly what's going on through here, but that refrigerant is seeing changes of state as it's absorbing and releasing heat. And it's picking heat up in the system and taking that heat to an area where it's not objectionable. But the compressor is the key component. It's the heart of that cycle. And there are lots of different types of compressors. Some of them are tall and thin. Some of them are short and fat. Some of them come with other components already included in them in the case of condensing units. But they're all doing the same thing. Regardless of what those compressors look like, they are all moving that refrigerant throughout the system. Now, a compressor is a pump. Well, we know what pumps are. Pumps move fluids. Well, not necessarily, not in the case of a compressor. I'm not going to move a liquid with that compressor, and I never, ever want to have liquid in my compressor. Now, we say that, and when we charge some of these compressors, let's say with 410A, we charge it by putting the refrigerant in the form of a liquid in the compressor. But it's changed very, very quickly to a vapor. and we do it very, very slowly as well. So now we have these pumps. Let's look at these pumps. They're all pumps, but some of them pump a little bit differently than what others do. If we look at reciprocating compressors, this would be a typical reciprocating compressor. You can see some of the components that are in this compressor. And there are lots of different components in here. And some of the components sort of sound like automotive terms when we hear crankcase, muffler. Those remind me of automotive terms, a cylinder head, a valve plate. So with a reciprocating compressor, that reciprocating compressor operates in a very specific manner. Now, when we talk about reciprocating compressor, we're talking about a compressor that has valves in it. This is a breakdown of a reciprocating compressor. And you can see those pistons moving inside those valves. And the motor is moving those pistons. And what's going on, it's taking the refrigerant and squeezing it into a smaller and smaller area inside the cylinder. So it's building up pressure. And that's what the compressor is designed to do, compress and build up pressure. Now we look at some of these valves, and if these valves get liquid trying to be moved through them, that's where we'll see failures in our compressors. So again, this is a typical reciprocating compressor. And we might see that then when this is assembled, you can see it combined with the condensing unit. Now that could be a reciprocating compressor, could be a scroll compressor, could be a rotary compressor. This is a typical scroll compressor. Now, a scroll compressor is doing the same thing a reciprocating compressor does. It's pressurizing that refrigerant. Now, when I pressurize the refrigerant, as I increase the pressure of that, the temperature changes in that refrigerant. And when that temperature changes in the refrigerant, it causes the refrigerant to change its state. So when we're going through our refrigeration cycle, we'll see changes of state of the refrigerant. And that's what allows for better heat transfer. So at different parts of that refrigeration cycle, the refrigerant is in the form of a gas. And it's always in the form of a gas when it leaves the compressor and when it goes back into the compressor. But then through the coils, I'll see that refrigerant change from a gas to a liquid, from a vapor to a liquid. So this is a scroll compressor. It operates a little bit differently than what the reciprocating compressor does. And up at the top of the scroll compressor, there's something called a scroll set. The scroll set consists of two different components. There is one component that moves. It doesn't turn, it orbits. It orbits within another section that is the stationary section of the scroll compressor. Now remember, on the reciprocating compressor, as my pistons were moving inside those cylinders, it was squeezing the refrigerant and creating higher pressure and higher temperatures in the refrigerant. Well, with the scroll compressor, that scroll set is what's squeezing the refrigerant. There's another view of the scroll set in this compressor. And this would be the stationary portion of that scroll set right here. So now the scroll set, if we look at this, pay attention to this, watch this closely. And look at the blue part. The blue part is the orbiting part. And notice that it is orbiting and not rotating in a circle. The red part is the stationary part. So if my refrigerant is coming in through here, you'll see that as that refrigerant is passing through my system, it's getting squeezed more and more and more into a smaller and smaller area, which will then create higher pressures and temperatures in the system. So watch this as it operates. So you can see the blue would squeeze the refrigerant into a smaller and smaller area, which would build up the pressure and the temperature of the refrigerant. So a scroll is doing the same thing as a reciprocating compressor, but just in a different way. Now we hear all the time, well, what's better, a scroll or a reciprocating compressor? You look at this chart, it makes a comparison between the two. And typically, if I see more stable temperatures, that scroll compressor does a great job. We might see that with refrigeration, a little more stability. But if I see a lot of variability in those temperatures, that reciprocating compressor is better able to handle some of those more variances than what we might see with a scroll. Could you replace a scroll with a reciprocating? Probably. Well, could you replace a reciprocating with a scroll? Probably. And there are other factors that come into play, and we'll talk about those in a little while. There's another compressor, and we see this one typically in smaller units, and it's called a rotary compressor. And with the rotary compressor, now this goes very, very fast. If we look at this, the way the refrigerant is compressed, darn it, sorry about that. This will rotate against the sides and compress that refrigerant. Let me go back because that should give us a little bit of a animation. There we go. Now, when we look at those colors, you can see the blue represents the refrigerant when it's a lower pressure or lower temperature, and the red represents the refrigerant as it increases its pressure and consequently its temperature. So there's a relationship between temperatures and pressures. And as my pressures increase, my temperatures increase as well. Now on these compressors, we may see these used in both air conditioning and in heating. Heating in the case of a heat pump. Now I'd mentioned that we never want liquid refrigerant in the compressors because that will cause the compressor to fail. Well, what allows us to use those compressors in both air conditioning and with a heat pump? Because you could use the same compressor in both an air conditioning system or in a heat pump system. And it's the reversing valve. So the compressor itself is not changing its rotation. The compressor itself continues to operate the very same way in both the air conditioning mode and in the heat pump mode, in the heating mode. But what does change are my coils. And by using a reversing valve, It changes the flow of the refrigeration, and that what was the condensing unit becomes the evaporator, and what was the evaporator now becomes the condensing unit when I use a reversing valve with that. So the compressor itself does not change how it operates when it's put into use as a heat pump versus when it's used as an air conditioner. It's strictly with the reversing valve, which will then change the flow coming out of my refrigerant or coming out of my compressor, and the flow of the refrigerant coming back into the compressor. So where it was going to my condensing unit, it now would go still to a condensing unit, but it was that coil was working as an evaporator previously. So that has no impact on the actual performance of the compressor when I use it in a heat pump mode. Now, what causes compressors to fail? And there are some major reasons for failure on compressors. So when you're looking at a bad compressor and you're going to replace that compressor, before you replace it, find out what in the world happened. Why did it fail? So that you can avoid that problem once you install a new compressor. Now, these are actual results of compressors that have failed and have been examined. And the number one reason for failure of compressors is the start winding. Now, there can be a number of different reasons for that. We'll talk about some of those reasons in a little bit, in just a little bit more detail. But the start winding can fail if I misconnect the compressor. If I connect a line, a source of power, directly to the start connection on the compressor, I'm going to lose it. It's going to fail, and it's going to fail quickly. So that can lead to start winding failure. Another reason for start winding failure is failed starting components. Things such as capacitors, relays, contactors. Some of you may not be aware of this. If you notice on hard start kits, they have a bleed resistor across the terminals of the start capacitor. Whenever you have a start capacitor with a motor, we're talking about compressors here today, so we're talking about compressor motors, there should always, always, always be a bleed resistor permanently attached across the terminals of the start capacitor. Now, the reason for that is because capacitors store and release electrical energy. A bleed resistor dissipates that stored energy in the start capacitor after the start capacitor has done its job and got the motor started. If you don't have a bleed resistor on the start capacitor, it stores a voltage in there. It stores electrical energy. So now it's not been dissipated, it's still stored in the capacitor. Now these start capacitors are going to be working with potential relays. The potential relay is normally closed. Once I energize my system, the potential relay will sense a voltage that is developed by the speed of the rotor inside of the stator of that compressor motor. The faster the rotor turns, the higher the voltage goes. That's called back EMF or counter EMF. EMF stands for electromotive force. So now when the rotor achieves its operating speed, that means it's got the load up to speed, my back EMF would attain a certain voltage. The relay senses that and then opens, taking the capacitor out of the circuit. And when it has the bleed resistor on there, it now dissipates that stored voltage. When my compressor does its job and it's no longer needed, it stops. And there's no more voltage going into the potential relay. And the potential relay will go back to its normally closed position. If there's no bleed resistor on the relay, there's voltage stored in that start capacitor. And when the relay just about comes to a complete close, there's arcing. That voltage is released across the contacts of the relay from the start capacitor. That will cause those contacts to pit, could also cause them to weld shut. And if they weld shut, the next time I try and start that compressor, I'm going to burn up the start winding because I'm not taking it out of the circuit. That's a very significant reason for failure on these things. Now look at the next finding. No defect. That's the second major finding when these things are tore apart. Well, how can that be? Well, maybe there was something that caused the overload to open. Maybe there was some problem. Maybe there was a problem with my charge, my refrigerant charge in my system. Perhaps there was another issue. Maybe there was a connection issue. Maybe there was a problem with my starting components. But if it causes that overload to go out and you check the compressor winding, it may appear that it's open and you might condemn the compressor. Make sure you allow enough time for that overload to reset. And a lot of you guys might put water over that compressor shell to help remove heat. Some of you might even put ice on there to help dissipate the heat. Now we look at the next reason for failure, and it's liquid related. Now notice the liquid related, and then look at the last finding, and that's moisture and contamination. What's the difference between liquid and moisture? Liquid is when there has been refrigerant in the form of liquid inside the compressor, where moisture is H2O, it's water. Maybe it's condensation. So there's a big difference. So the liquid related comes from allowing liquid refrigerant to get back into the compressor. That could come as a result of an overcharge. That could come as a result of not having a heater on the crankcase. And when there's no heater on the crankcase, you might get migration of liquid refrigerant back into the compressor. So especially in the Michigan area where we get some pretty cold weather, we want to make sure that we get, we're using crankcase heaters to eliminate any possible migration of refrigerant back into the compressor. Now the moisture could come from perhaps I didn't take a good vacuum when I installed the compressor. Perhaps if I made a solder connection on my system and I was using a wet rag to keep it cool, perhaps I got some of the liquid from the wet rag, that moisture from the wet rag, into my system. So after installing a compressor, it's absolutely critical that you take a very deep vacuum on the system to make sure you have all of the moisture out of it. And then carbon buildup can come from a burnout, for example. And if you're changing out your compressor, and if you don't clean up that compressor and make sure all of that carbon buildup is out of the system, you're going to cause that new compressor to fail as well. But these are the major findings that we see with compressors that have been returned. Now, there are some checks that you can make on your compressor to see if it seems to be operating okay. And if we look at the top part of this slide, we'll see that if I check my start line, if I just use my multimeter, my clamp meter, and put it over my start, when that compressor starts, and if it has a run capacitor only, no start capacitor, just a run capacitor, the run capacitor stays in the circuit the entire time that the compressor is operating. But you'll see that those amps are going to be between 2 and 8 amps. That's a good indication the compressor seems to be operating okay. I would see a little higher amps upon startup, and then they drop down and operating within their full load amps that are shown on the nameplate. If I have a run capacitor and a start capacitor, and if I check my starting amps, they're going to be very high when the motor starts. But when the motor, the potential relay takes the start capacitor out of the circuit, those amps are going to drop. So I could see them about 20 amps when first starting, and then dropping down to about 2 or 8 once it gets started. If I have a start capacitor only on my system, when I check the amps, I'll see very high amps when it starts up. But there's nothing else in that start winding except that start capacitor. And so once the motor gets up to speed and the potential relay takes it out of the circuit, it drops to 0. And that's an indication that it's operating properly. Now I can check those windings also to see if they appear to be okay. Now notice this is what the winding of the motor would appear as. These represent coils in the motor of that compressor. And this is the start winding. This would be the main winding. The start winding is generally going to be a higher resistance. Its wire size is probably a little bit thinner than the wire size of the main winding. And so I might see a higher resistance on the start, lower resistance on the main. My common is going through the motor protector. Now, if I'm measuring from here to here, I'm measuring through my start winding when I'm measuring my resistance. If I'm measuring resistance from common to run, I'm going through the main winding. Now, as a result of that, I can check my winding to see if it's operating okay, or if it appears to be okay by checking my resistance, just doing a continuity test, putting your multimeter on ohms and measuring the ohms. So if I measure the resistance from common to run, that's going to be my lowest resistance that I measure during this test. If I measure the resistance from common to start, remember this winding is a higher resistant winding, the start winding, than the compressor. So it's going to have a greater resistance when I measure from common to start. It's going to have a higher resistance when compared to common to run. What do you think happens if I measure resistance from run to start? That's going to be the greatest resistance of all, because I'm going through both of those windings. And there's a characteristic that if you were to measure resistance from run to start, it's going to be about equal to the resistance of common to start added to common to run. There may be a slight distance because of the resistance through here, but that's going to be a very close example. So if you find that your resistance is okay, your windings appear to be okay. Now, another benefit of this is if I can't read the nomenclature on my compressor and I can't tell what common, start, or run is, by taking these measurements, I can identify what those three terminals are. If it's a three-phase compressor, and when I measure the resistance from one leg to the other legs, and measuring that resistance from one leg to every other leg, that resistance should be within 3% of each other. Now, when we talk about ECMs, electronically commutated motors, they have you take resistance readings on those. That resistance is a little bit different. It's a little higher. They allow a little more resistance than they do on a compressor. So on a compressor, it should be within 3% of each other. Have you ever heard this? Always disconnect power to the compressor prior to removing the terminal cover on the compressor. Voltage should never be applied to a compressor when the terminal cover is removed. Well, why would that be? When I apply power to the compressor, what does the compressor do? It compresses. It builds up pressure inside of itself. And the reason you never want to put power to this without having the cover on it, those pins in those terminals are attached to the compressor through a glass-like material called fusite. And we all know that glass can be kind of delicate. And if that compressor gets knocked around, if it's been rolling around in the truck, or if maybe you've hit that compressor with a block of wood or a hammer to try to get it started, you could damage the fusite. If that fusite is damaged, and if you put power to that, forming high pressure inside of the compressor, those terminals could shoot out of there like a .22 bullet. And people have been killed by that. So always, always, always make certain that the cover's on the compressor when you're testing it. Now, we were talking about the liquid scenario and how we don't want liquid in the compressor. Now, that's contrary to when we're charging it with 410A, because we charge it with liquid. But with that, when we're charging it with the 410, we're doing it in a very, very small amount, very slowly, and it's leaving as a vapor. So now we can be assured that we don't have liquid returning into the compressor through my suction line by testing for something called superheat. Superheat assures that if I've got superheat present, the refrigerant going back into my compressor is all in the form of a vapor. It's all a gas, and that's what I want. And so it's important to verify that you have superheat, assuring that you don't have refrigerant going back into the compressor as a liquid. Now, superheat is a measurement, and it's a measurement comparing we call it, if we look at a pressure temperature chart, and we see the pressures and temperature on the pressure temperature chart, that represents what we call saturation. With a pressure temperature chart, depending upon the pressure that I measure in my system, there is a temperature associated with that pressure, and that temperature associated with that pressure is called the saturation temperature. And the saturation temperature is when I have refrigerant. Part of the refrigerant is a vapor, part of the refrigerant is a liquid. If I increase the temperature of that refrigerant by a degree, it all becomes vapor. If I reduce it by 1 degree, it all becomes liquid. When we increase it, when the temperature is higher than saturation, that's called superheat. When I decrease it, and at that point, when I decrease it, it all becomes liquid. That is called subcooling. So subcooling is also a reference to my saturation temperature of the refrigerant. If I look at a pressure temperature chart, and a lot of you have gauges now that give you this, that show you that. If you don't, I think Behler-Young probably has those available. But those gauges make it very easy then to determine that you have superheat and subcooling. The superheat is going to tell me I do not have refrigerant returning to the compressor in the form of a liquid. Subcooling is giving me an idea of my charge of refrigerant, that I'm not overcharged, and I'm not undercharged. Now let's look at this chart and look at the refrigerant R410A. Now let's just go down under 410A to a pressure of 121.2. So if I were to measure that pressure when I'm determining whether I have superheat or subcooling, and I go over to the left, that would show me that at 41 degrees, that's the saturation temperature. That means that my refrigerant, when it's at saturation and the pressure is 121.2, the temperature would be 41. Now, if I measure, and I measure this after the evaporator and before the compressor, if I measure my pressure and my temperature at that point, it'll show me my saturation. But then let's say that I measure the actual temperature of the refrigerant before it goes into the compressor as 51. The saturation temperature is 41. I measure 51. That shows me I have 10 degrees of superheat. That means that my refrigerant going into the compressor is in the form of a vapor. Now, you always want to make sure that you're using the manufacturer's requirements for what the superheat and subcooling should be. When I measure the subcooling, then if I were to measure the actual temperature at 31, then I would have subcooling. And again, we use that a lot when we're determining our charge in our system, but always follow the manufacturer's suggestion for that. I think I might have said that I measure the superheat on the liquid line. I measure that on my suction line between the evaporator and the condensing unit. And I measure my subcooling on the liquid line. I'm sorry if I confused anybody on that. When I've determined that my compressor needs to be replaced, then I have to select the proper compressor. Now, one thing I can do is look at a cross-reference. And maybe even before that, see if I can get that same part number. But maybe that same part number has been discontinued, or maybe I just can't get it. Maybe I can't get it for a month. So then I can look at aftermarket replacements. And I can take the information off of the old compressor and use cross-references. Now, Packard has cross-references available on our website that can help with that. But even if a compressor doesn't cross, it doesn't mean you can't get a replacement that's going to do the same job in that system. But there are some characteristics we want to look at. First of all, we want to know the application. The application is going to tell us a number of different things. First of all, if I've got an application of a freezer versus an application of an air conditioner, I probably have a different refrigerant that I'm using, because not all of these refrigerants perform the same way. And so they're designed to be able to provide me with the temperature differences that I need for the particular application. So there are target temperatures that I'm trying to meet. And some refrigerants don't do as good a job in some of those applications as other refrigerants do. So I always then want to make sure that I'm selecting based upon the refrigerant that's being used. Well, why can't you just put a different refrigerant in a compressor? Some refrigerants operate at different temperatures, but they also operate at different pressures. And if my compressor isn't designed for example, the high pressure of 410A, I could destroy the compressor because of those higher operating temperatures. That may never be able to reach those temperatures without causing a failure in the compressor. And so I need to match the refrigerant then, understand what the refrigerant is, and then select a compressor that is designed for that refrigerant. Of course, I always want the correct voltage, the number of phases, single phase or three phase, the frequency. Over here in the US, it's typically going to be 60 hertz, unless we have some of the variable speed compressors that we're seeing today. And those are designed a little bit differently. But then we want to select a compressor that is going to be able to give us the capacity that we need. And typically that capacity is rated in BTUs, British thermal units. Now we want to make sure when we're selecting the compressor that we're not going beyond 10% above or below the rating of the original compressor. And this may seem unusual, but sometimes it might be better to select a compressor that is maybe a little lower in BTU rating than the original. Again, not going beyond the plus or minus 10%. An example of this is I replaced my unit, and my original unit was a 310. But then the ductwork in my house, which had already been set, was such that I wasn't getting cooling in one of the back bedrooms. So what we wanted to do is to keep that compressor running a little longer. So by putting a smaller compressor in there, it ran a little bit longer, and it was able to cool that back bedroom much better than with the larger compressor. And the thermostat was not in that back bedroom. So that helped. Another thing we want to look at is fit. It's got to fit. Now, I mentioned earlier that you may be able to replace a scroll compressor with a reciprocating, or you may be able to replace a reciprocating with a scroll. But the thing you have to be sure of is that it is going to fit in there. It's not going to be too tall or too fat. Now, the refrigerant, they're very different. So we have to make sure that we're matching the refrigerant that the system is designed for. Not only for that system itself, but the compressor may have an oil that may not be compatible with certain refrigerants. Now, as we're moving away from R22, we're seeing more of the POE rather than some of the mineral oil. And we're eliminating some of those concerns over that oil because the compressors are being designed for that. So that lubricant's important, the valves and bearings. I'm not going to go through all of these different characteristics that are important just because of the time span that we have. So this presentation has been made available to you in a PDF format, and then also we will have a recording of it. But feel free to go back and look at some of the other considerations that are really, really important in the design of the compressor when we're selecting that for a particular application. We've seen lots of changes in the types of refrigerants that are being used over the years. And the changes are really resulting from the impact on the environment. So we've seen a change from the chlorofluorocarbons, and those contributed to greenhouse reduction. And then also hydrofluorocarbons. Notice that both of those contain chlorine or chloro component of them. And that's been damaging to the ozone layer. So now we're getting away from that, the hydrofluorocarbons. But this is going to change as well. And we've seen changes in refrigeration with some of their refrigerants, where they've gone to some of the natural refrigerants. And the natural refrigerants, one of the key components that we look at of our refrigerants is something called GWP, or global warming potential. And some of our older refrigerants have had a higher global warming potential, but our natural refrigerants like R290 and R600A have a very low GWP, and they can even be vented into the atmosphere safely. But a concern about them is that there is flammability associated with them. It's low flammability, but there's still precautions that need to be taken as a result of that. But we're seeing a trend towards this, and we'll see it on the air conditioning side as well. So when we look at the ratings of some of these newer refrigerants, we see the flammability rating, but we also see a toxicity rating on them. The newer refrigerants, propane, for example, it's not the same propane you use in your gas grill. So do not try and use that in there. You'll damage your system. But the flammability, typically the amount of refrigerant we have in there is about equivalent to 2 or 3 Bic lighters. And it does have a relatively low flammability ability to it. So we're trying to save the environment. That's why we are going to these natural refrigerants. And they're going to have an impact on compressors, and they'll probably give us longer compressor and system life as a result of it. Again, I'm going to move through some of these relatively quickly just because of the time constraints that we have right now. So we'll see similar performance, similar displacement, similar operating pressures. Some of the lubricants are going to be the same, but there will be changes in components. Components will have to be non-arcing so that it doesn't cause the chance for a spark to cause a flame. And it may be worthwhile then that you use a fan in the area so that you can blow any refrigerant that could possibly have escaped away from the area so you don't have any hazard of flammability. You also may want to put a safety placard out, something identifying that you are working with flammable refrigerants. So these are things you're going to be exposed to. And if you're in refrigeration, you may be seeing these things already. But it's going to be important to be safe and make sure that you're just aware of it and taking some precautions. You might want to have a gas detector right there at the site at all times, always turned on, so that if there is an escape of gas, you're aware of it. But again, if you have a fan blowing that out, you're not going to have any danger. Charging hoses going to be a little bit different. You want something very small because these charges are very small. And because they're small charges, you want short hoses. And you'll be weighing these refrigerants in using a scale. And you need to have a very accurate digital scale used for this. And as we mentioned with the electrical components, they're going to have to comply with safety regulations so that they do not create a spark in operation. Now, when we talk about the capacity of compressors, we talk about BTUs. Sometimes you'll see this in tons. Sometimes you might even see it in horsepower. But 1 BTU is the amount of energy needed to raise 1 pound of water by 1 degree Fahrenheit at sea level. Sea level because of pressure. There are 12,000 BTUs in 1 ton, and there are 1 horsepower is equivalent to 2,544.4342 BTUs per hour. So there's a relationship between those. Sometimes people will refer to 1 ton equivalent to 1 horsepower. That's not necessarily true. And the same with 1 BTU. It's not true that it's equivalent to 1 horsepower. So this little chart makes it easy to convert horsepower to BTUs. But typically you're going to be selecting these based upon BTUs. That's more accurate than trying to use ton. We talked a little bit about the capacitors and how they're very important to make sure that my starting components are all operating properly. And if you have a start capacitor in the system, be certain that you permanently attach a bleed resistor to that capacitor. You want your capacitors to meet the rating of the motor of that compressor so that it is operating properly. And you can test the capacitance using your multimeter in most cases, or capacitor tester, just by setting your meter on microfarads on capacitance and measuring from common to, in the case of hermetic for the compressor, to the hermetic, or if you're checking the condenser fan motor from common to fan. If it's a single rated, just measure your microfarad rating across the two terminals. And it should be within the tolerance shown on that particular capacitor. In the case of a start capacitor, it should be within the range shown on that start capacitor. You can also measure the capacitance when the unit is live. And I'm not going to go into detail on this because of the time constraints that we currently have. I'm running over a little bit right now. Always use the correct capacitor. Do not put one of a different microfarad rating on there. So always use the correct microfarad rating, but you can go up in voltage. And it doesn't matter how high up you go. As long as the capacitor is rated its voltage rating, at least what the motor calls for, you'll be okay. And that capacitor voltage is a result of back EMF, that counter EMF, the electromotive force that the motor creates as the rotor is turning in the stator. This is typically what we see inside of capacitors. There's now a capacitor out there that is using a segmented film, and this segmented film gives us a little bit better reliability over time. And that if I see a catastrophic failure with this could help prevent that. So if I see a voltage surge, that voltage surge could destroy this capacitor. But with the segmented film, it may only lose segments of that film and may not completely take the entire capacitor out. So for some applications where life is critical, where I can't afford a catastrophic failure, this type of film may be an advantage. A start assist, that is just a start capacitor with the relay attached. Now, in addition to the potential relays, sometimes we will use voltage. That's the voltage sensing relay, the potential relay. But sometimes we'll use, pardon me here, we'll use amp current sensing relays, and we'll also use temperature sensing relays. So in some of the smaller systems where we're using those temperature sensitive relays, if you have situations where you could see cycling, short cycling of these systems, maybe with an ice machine that's outdoors in the summer months, there could be a lot of demand on that. And those temperature sensing relays may not always reset themselves quick enough to give you the performance that you need. So just be aware of that with those relays. On the contactor, typically the crankcase heater is connected on a single pole contactor on the shunt side of that contactor. With this, I would always have power from this side of the contactor to that side of the contactor, from my load side to my power side, my lead side. So that would always be hot. Now, we want that with a crankcase heater because we always want the crankcase heater to provide heat at the lowest part of the compressor, the crankcase, which can help prevent migration of liquid refrigerant back into the compressor. A lot of guys like to use two-pole contactors rather than single-pole contactors. And when they use a two-pole contactor, they open and close both legs of that power. So now if you put your crankcase heater on this side, and this is my line, sometimes my crankcase heater is going to be hot, sometimes it's not. And when my compressor is not running, that's really when I want it to be hot. So can you use a two-pole to replace a single pole? Yes. But now put your load, the crankcase heater, on the same side as your line. And then being on the same side of the line, it's always going to be hot. Well, I've gone a little bit over, and I'm sorry, I've went fast through a number of these slides, but we've covered a lot of information. I hope I've given you a little bit of content to think about. And if you have questions on this, feel free to get with us. And if you have questions, ask me now. Is there anything else that we can do? We have a website you can go to, and some of these things are covered on that website as well, in some of our YouTube videos. Do you have any questions?
I got a quick question for you.
Certainly.
So a couple of years back, I had a class on these compressors as well, and the gentleman was telling me that once we take off our gauges, if we're getting oil by the ports, we need to look more into the superheat. What is your stand on that when we take our gauges off and oil is coming out? Like not a small amount, but a decent amount of oil is coming out when we take our gauges.
I think that too much oil in that system could be an issue with that, and that would affect my temperatures. There's going to be a temperature with the oil versus the temperature that you might see just with the refrigerant. So I think that that's probably a good point. That could affect the temperature of that superheat. And that's one thing that we look at also with our TXVs when we install a TXV on that, because that TXV is going to be operating based upon pressures and temperatures, which can be affected by oil logging in that thing.
Gotcha. Thanks, bud.
Sure, you're welcome. Anything else? Justin, is there anything that you'd like to say? Justin Spalding is our regional manager in your area. And you may see Justin around from time to time, and feel free to pick Justin's brain. And if you have questions, Justin will be sure to get you answers for your questions as well. So please feel free to get with him. Justin, do you have anything you'd like to add?
No, Rick, I don't. Certainly appreciate you doing this, and appreciate everybody joining the call here, and hopefully, got something to take away from this. So certainly appreciate everybody joining, and Behler-Young for setting this up.
Certainly do appreciate that. Tony, is there anything that, any comments you'd like to make? Anything else you'd like to share?
No, I'm good, but I just wanted to thank you for taking the time today, Rick, and I thank all the customers that came on board this morning. We got some nice rain here, so I don't know how much field work was being done, but I do want to remind you all that this is being recorded, and you can reach out to your TM. We are going to post on the website, and they will find you the link. So thank you again, Rick, and thank you all for attending.
Our pleasure, and thank you so much, Tony, for having us in today. And we're here to support you guys, so let us know if we can help with anything. And if anybody is NATE certified, and if they're looking for an hour of NATE CEU, if you can provide us with that, you might be able to provide that to us through Tony. If you provide that to us, then we'll get this entered into your record, so you'll get 1 hour of NATE continuing ed credit for this. Thanks so much, folks. Again, thank you, Tony.